Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to help you out with number 69, chapter 10 in the University Physics text, the OER text. And what it is, it says something about a force applied to this sphere, which is free to rotate in this direction. Now, the reason they're even mentioning a force, that's what it would take to get this thing moving. This force is not actually relevant for the question. Right? The question basically is this. At the instant shown, this sphere is rotating about this axis at some speed. Now it says the center of mass is moving this direction at 15 centimeters per second. This is free to rotate, so what's going to happen is that center of mass is going to rotate up to some position here. So I'm going to go ahead and draw some geometry here. If I draw a vertical line, actually I'll make it a dashed line like so. Draw the same dashed line over here. The center of mass has now moved up so that we have some angle now. And this is basically a kinetic energy to potential energy situation. If you watched my previous video, the way you don't want to handle this is don't try to draw a free body diagram here and try to find maybe the angular acceleration, because the angular acceleration in this problem is not constant. It's not that Newton's second law can't be used on this problem, but the math to solve it is typically beyond the scope of this class. What you want to do instead is work energy. I would call this position 1, this position 2. Now, in the problem, this is the highest location here, so the angular velocity here is 0, and that means the kinetic energy in this picture is 0. The potential energy terms are going to be dependent on where you put your datum. I strongly suggest you just put the datum here, right through the axis of rotation. The axis of rotation tends to be a very nice place to put a datum with rotational problems. So your PE1 term, you're going to need this distance, which is the radius of the sphere. So your PE1 is going to look something like minus mg times r, the radius of the sphere. In picture 2, the distance you're going to need is this distance. Oops, I'll go ahead and draw that in green here. You're going to need this distance, that vertical distance here, again, to the center of mass, that guy. Now, this triangle right here, the hypotenuse is r, the radius of the sphere. This distance is adjacent to theta. So your PE2 term, it's going to be minus mg times something. I'm not going to give you the something. I'm going to let you figure this out. This is your homework problem. But again, the distance is r. The distance you need for the potential energy term is adjacent to the angle theta. Right. Let's go back here to picture 1, the KE1 term. The easiest way to express the kinetic energy in picture 1, the KE1 term, is going to be with a rotational term, 1/2 I omega squared. Both of these animals, you're going to have to actually calculate or do a little work. Let me take the moment of inertia first. This is a spherical object. Look up the moment of inertia of a sphere about its centroid. And I'm going to let you do that. I'm not going to give that to you in the video. Just look it up. That's going to be some value. But that's the moment of inertia about the centroid. We need the moment of inertia about this axis. So what you have to do is you have to apply the parallel axis theorem, PAT. PAT basically says the moment of inertia about any axis of any geometry is equal to the moment of inertia that goes of the geometry about its own centroidal axis, plus an mr squared term for the fact that the axis is moved. So in this example, the moment of inertia about this axis is going to equal the moment of inertia about the centroid, which you can look up, plus an mr squared term for the fact that the axis has moved from here to here. Right. The angular velocity now. The 15 centimeters per second is a translational velocity. At the instant shown, right, the center of mass can be thought of as rotating about this point, moving along a circular path like this. This velocity is equal to r times the angular velocity. Now, to be consistent with units, I would write this as 0.15 meter per second and use your r in meters. So you should be able to calculate a numerical value for the angular velocity at position 1 You're going to use that here for the KE1 term, and you're going to use an expression something like this for the moment of inertia term. So that should be enough to get this done. Get it all put together, write out your work energy theorem, and glance it over for the unknown. I believe there'll be one unknown when you get done with that. So hope this video helps you get a good running start at number 69. Have a great day.